Siwei will go through one example for the last lecture and for several examples in more detail. Yeah.
Thank you, and thank everyone for being here. Now, before I start, I have to apologize that I got a cold last night. I hope my voice is still clear to everybody in the room. Can people in the back hear me? Clear enough? Good, excellent. Now, I outlined my lecture plan on this blackboard. So in the first lecture, I wish to cover the simplest possible quantity in a defect CFT you can ever ask, that is the one-point functions. Now in lecture 2, I'm going to discuss the two-point functions. I feel lucky that I only have 2 lectures, so I can stop right before anything gets complicated. And for examples, we are going to discuss some free series models, free boson and free fermion, which is possibly the most simple QFT you can come up with. And in the second part of the second lecture, hopefully I can tell you something new that is in the gauge field, which is 4D Maxwell. If I feel to have to cover that, I would invite you to focus on the archive mail list. This will come up as a new paper very soon. Okay, I want to start with some general remarks about the CFT and our hero of the story, that is the DCFT. So the CFT in a d-dimensional Euclidean spacetime has a conformal symmetry, which is SO d plus 1, 1, where d is dimension. Now, if you insert a defect, which I denoted as that occupies a hyperplane of p-dimensional and occupy the coordinate, which I denote as x parallel, it breaks the conformal symmetry down to a subgroup, which we call the SO p plus 1, 1, which also introduced by Zohar. Now, if the defect is anisotropic, we also expect it to preserve the transversal rotation symmetry, which I denoted as SQ. And here the convention is such that P plus Q equals to D. Okay. Now, CFT is a very successful formalism, and particularly if you want to consider one-point functions, you would very soon find out that they are trivial. They has to be identically 0, unless the operator dimension is 0, which means it is a topological point operator. This simply follows that there's no dimension for quantity in the CFT. So there's nothing except 0 you can write down in the right-hand side of this equation. So this part is trivial. Now for the two-point functions, things start to get interesting. And these two-point functions are usually fixed completely by the conformal symmetry up to some overall constant. And this constant, some of them encode many important physical information about the QFT. For example, the two-point function of the stress unit tensor. This would tell you when d equals to 2, the central charge. Okay? And in other dimensions, for example, 4, it tells you the conformal anomalies, which are known as the A coefficient and the C coefficient. Why are they useful? Because this, for example, the C central charge is an RG monotone for 2D QFTs. It monotonically decreases along the RG flow. So you can use that to, as Zohar just showed in the last lecture, to tell if some theory could flow to another or cannot. Now, for the three-point functions, they are still fixed by the conformal symmetry, and the coefficient of this three-point function is what is known as the OP coefficient. Let me denoted as O1, O2, O3, okay? OP. 4 point, okay, we lost control because you can build cross ratios. Now, if you are an expert in bootstrap, that's where your technique would come into play. Now, the story becomes a little bit different for defect CFT. For example, the one-point function now can be non-zero, and we're going to discuss a particular one-point function that is one-point function of a continuous current, which for this very specific defect could tell you the G function, the defect entropy, if you have learned that name in the last lecture. G when d equal to 3. And more generally, when d equal to 4, you can obtain an analog of the G function, which is known as the B coefficient. It's also a RG monotone, which is also introduced in last lecture. Okay, for the two-point functions, you can start to build some cross ratios. So usually it's not fixed. for if both points are in the bulk. Okay, so that's, again, bootstrappers could start to come up with some answers. Now, if one of the points are in the defect, in this case, we are lucky enough that, again, this function is fixed entirely by the conformal symmetry up to some constant. And these constants, which I denoted as C, O, O hat, where hat representing operator on the defect, is known as the bulk to defect of B coefficient. Now, 3-point functions, complicated. 4-point functions, also complicated. We are going to cover the 1 point in the first lecture and the 2 point of this kind in the second lecture. So you can really tell that I hate cross ratios because I can do nothing about them. Okay? Any questions? So what's so good? Yeah, please. Oh, J represents a current operator of a continuous global symmetry. I will tell you why this is useful in these particular twist defect models. I will explain what is twist defect. I hope I got the time to do it. Okay. Now, when I say that these 1-point, 2-point functions are fixed by the conformal symmetry, it's very natural to ask how. I mean, why? To what extent they are fixed by the conformal symmetry? To solve that, to solve the constraint from the conformal symmetry, we need to come up with a good formalism that I introduced now, that is known as the embedding formalism. Okay, I hope I didn't spell it wrong. The idea is to map the point in the real physical space, which is Rd. This is a point, to an array of non-points in an embedded space, or I should say in Rd. And now it becomes arrays of points in a larger space-time, which is d plus 1, comma 1. That is Euclidean space-time. And the map explicitly is you can take a slice, which is known as P, and the coordinate is M. So anything that is proportional to this very specific point, 1 x u contracted x u. So here this is a d-dimensional subspace, and there you have 2 extra dimension, and in total you got a d plus 2 dimension. Okay, where the metric is such that in the light core coordinate is such that. Okay, now you can just verify from simple algebra that the norm of this vector is identically 0. Just x squared minus x squared plus x squared equal to 0. Okay. Okay, you can start complaining now. Why? Why should I do this? Why even try to embed this point to this very exotic subject? So the idea is that the conformal symmetry now becomes the isometry of this larger space-time, which is SO d plus 1, comma 1. Now, as long as we make sure the indices of these array points, which I denoted as capital M, are properly contracted, you would recover the full conformal symmetry. So now you have just to do undergraduate linear algebra to make sure the conformal symmetry are restored. Okay, now let me introduce the subject that we would like to know. When we talk about 1-point functions, what 1-point function specifically that we want to know? We would like to consider more generally, most generally, a spin J operator. Which has, in the real physical space, let's say it's O, different vector indices, mu1, mu2, all the way down to mu_j, that is fully symmetric and traceless. Now, you can use this map, which I wrote down here. It is 1-to-1 correspondence. You can use this map to map these spinning point operators to the embedded space. and they have the indices capital M. So right, maybe I should skip this. It's really some simple linear algebra. That actually is not helpful. You're just making the spinning operator in a more complicated form that is in the embedded space. Now, the standard trick to start it is to introduce what is known as the polarization vector. That instead of starting this very complicated tensor structure, we will try to start some polynomials defined as follows. Capital Z so far so good. There's no physics here, which I'm sorry. It's just a pure mathematical trick. I promise we will come to physical examples very soon. So please don't fall asleep. Now, okay. Now we first know that we are not mapping points to points. Instead, we are mapping the point in the real physical space to an array of non-points in the embedded space. So that means this map has to satisfy some consistency condition, because I could have chosen another point along the array, and that should also do. And that is what is known as the transversality condition.
Sorry, so you said we're mapping them to null arrays?
What?
I mean, did you say we map them to null arrays?
Right. Every point on this array, where lambda is some real coefficient. Right. So to make that map,
does the array have to be null?
Yes.
Okay, so ds squared is 0?
P squared is 0.
Okay.
Because now we can, okay, so the first two indices, you can call this x plus as it here, x minus as it here. These are the x mu's. Now we can just do the algebra. Right. Now, I could have choose any other points along the array. And that means my tensor, the embedded space, had to satisfy certain conditions, which is known as the transversality condition. That is, if I contract this O with any other P, let's say Pi, well, it's fully symmetric, so it doesn't make any difference. This one has to be 0, because you can just do a small displacement along the array, and this is what you will get. That has to vanish. And also, this operator has to be traceless, as we are considering the spin J operator in the Hilbert space. Sorry, not in the real physical space. Let's say M1, M1. This has to be 0. Now, for this auxiliary polarization vector Z to be ever useful, the transversality condition means that Z has to be null with respect to P. And for the tracelessness to be satisfied, you would have to require that Z itself has also to be null. Okay? So these two conditions are what we impose by hand to make this formalism useful. Otherwise, you would introduce some unphysical degrees of freedom. You can, in general, think this Z as a complex vector. It does not have to be real, as long as it helps you to track all the spin structures. Now, the very first thing that you would notice is that Z definitely is non-unique. Because if I come up with Z, let me just come up with 1. That is 0 to where I have introduced small z. Okay, the capital Z and small z is not obvious. Maybe it's capital. Where this real space Z has a complex vector satisfy the null condition. Now we can just verify the inner product between the Z and the capital P is identically 0. Such Z's are not unique because you can always shift this by something that is proportional to P, and these two conditions are always satisfied, right? That means for us, if we want to try to write down any physical meaningful polynomial in Z, it must show up in a quote-unquote gauge invariant combination. And one such combination is what I call C. I'm just running out of notations, so forgive me for that. All right. So this is a degree of Z that is of, this is a polynomial of Z that is of degree 1. And you can clearly see that the shift is by P, since P itself is null, I will not change this gauge, quote-unquote, gauge invariant combination building blocks. Now, let us come back to the spinning operator that we care about. So here, I'm contracting this operator with J different of J, J different of Z in total. So this object, OJ, should be a polynomial of degree J in Z. And since this is the only building block that we have that is gauge invariant to write down this polynomial, you can ask, okay, what are the possible combinations that I can ever write down? Well, this object does not have any indices, so all the indices have to be contracted. But very soon, you will find out these building blocks, when contracted together, is identically 0. That means there's no meaningful polynomial that you can ever write down. That means in the CFT, where the defect is absent, the one-point function has to always be 0 for any spin J operator, which is a well-known fact. Okay, any question for now? Is it obvious why this has to be null? Because Z has to be null and Z is null with P. All right? Okay, what is different when you have the defect? Okay, maybe it's right here. So when you have a defect, let me repeat the symmetry breaking pattern for you. These fundamental tensor building blocks, C, split into 3 different classes. Now I could have both indices in the first P, in the first SO, in the P plus 2 dimensional subspace. That means I have, I can also have one indices in the P plus 2 subspace and another indices in the Q dimensional subspace, and or both indices, A1, A2, in the Q dimensional subspace. Here I'm using the convention that N transform under SO P plus 1, comma 1, and A transform with respect to SOQ. Okay? So yeah, I'm just making things even more complicated because now instead of one kind of tensor building blocks, we're having 3. Okay, so that's good. Notably, these tensor building blocks are not independent of each other. Now, since this P point is the only element that you can use when building a one-point function, they have to contract with each other. Now, you can prove maybe I should leave this as an exercise. That for any vector satisfy the following condition. That they are known with respect to Z and also known with respect to P. For example, you can take R1 or R2 to be Z or P or any other combination. You can verify that these tensors are not independent. They are linearly related with each other, as long as they can track with themselves. Okay? So the good news is that we don't have to bother with all three kind of tensor structures upon this the branching of this conformal group. The good news is we have to care about one, and we can pick one. And here we can pick it to be A1, C, A1, A2. Okay? So did it clear why this relation shows that they're independent? Yes? No? Okay, I take that as yes. If you have complaint, tell me afterward. Okay, so the only tensor building block that we have here that is independent is C, A1, A2. And remember, for a spin J polynomial, oh, did I erase that? Okay, for the spin J polynomial that is defined as this, so this object, this polynomial has no indices, so different indices have to be contracted with each other. And you can clearly find that CA1, A2, when contracted with themselves, okay, which is something you can also verify ahead by taking this condition. And this means that this polynomial is nothing but this object to the power of j over 2. Okay? Okay. You may complain this is too abstract, this is nonsense. It is actually not, because now you can take some physical examples, which I'm doing now. Okay, I'm running out of time. I will leave this as an exercise to go back from the embedding space to the real physical space, to use this polynomial to find out what are the real space coordinate component of the spin J operator. Now, for example, I'm going to take Q equal to 2. The codimension is 2, such that the defect itself is D minus 2 dimensional in real space. And I'm going to take a polar coordinate. Where is Taro? And you can find that for j equal to 1, it happens that the square root, oh, where did I wrote that? Yeah, here this square root can be solved, and it is indeed a polynomial in Z. And you can find out the spin 1 operator in any DCFT has to be such that now it has only one indices, where delta is the dimension of this operator, and the small delta is the coordinate delta function. So the only component that could pick up above is the azimuthal component, while other component has to be identically 0. Now, for j equal to 1, you can take a special case where delta equal to d minus 1, which means this operator is actually a conserved current. This fact is simply saying that the one-point function of the conserved current can only be that the current are circulating around the codimension 2 defect in the theta direction. There could be no radial direction r equal to 0, because otherwise that means the charge will start to accumulate at the location of the defect. But actually you can see that you don't really need charge conservation to see a problem. This is already fixed by the conformal symmetry. Okay? Any question? Oh god, I'm seeing a lot of confusing faces. Now for j equal to 2, which we are also going to discuss, you can do a similar thing. And the result is such that this spin 2 operator has to be it has to be diagonal matrices. And again, it is fixed up to one single overall constant. And the actually physically non-trivial component is the O theta theta component, while others are just trying to make sure the entire combination is traceless. And for example, you can take this operator to have d equals to d, sorry, delta equals to d. That is the stress energy tensor, and that simply tells you how not every component can pick up a VAF with the presence of defect, but instead only this diagonal component in the polar coordinate can do that. Okay, any question?
Could you repeat what you just said?
Okay, I'm saying that the one-point function of the stress energy tensor in the presence of a defect, not every component of this tensor can pick up a VAF. Instead, only this diagonal component can do that. All right? Sorry, a diagonal component in the polar coordinate. It's essentially this t theta theta. Pick up a VAF. The others are just trying to make sure the entire tensors are traceless. Okay.
Sorry, just confused why so non-homogeneous in the dimensional parameters. So you have the diagonal part with as constants and then r squared.
Oh, yes, because theta is dimensionless. I'm using this polar coordinate. So here is r.
Theta is dimensional.
Yes, I'm sorry for that.
And the last one is theta. So
Yeah, so the t theta theta differ by other components by r squared or 1 over r squared in some notation. All right? Okay. That's how the conserved current and the stress energy tensor looks like. Now I'm going to start discuss this. Finally. The physical model that I would like to discuss is twist defect. Okay, so yeah.
To root 1 over r to the delta, is that a 1 or can I have
Sorry, where?
a coefficient?
Where? Here?
Yes.
I'm saying that this. Okay, you can say this thing is fixed by some overall coefficient. Let's say A O. It's just to fix the tensor structure up to one overall constant. And I'm going to tell you that the constant actually tells you the physical information of the defect. All right. Okay, I have to be. Do it here. So I'm going to discuss a very special case of defect, which is known as the monodrome defect or twist defect. So So the construction is as follows. But we already know a zero-form global symmetry of a QFT is implemented by a codimension 1 topological operator. Let's say this operator is labeled by a group element G, which so what you essentially did is just to integrate the current operator along a codimension 1 manifold. So this operator is topological, nothing interesting, it's not conformal. What it is interesting is that if you let it to terminate at a boundary, at a codimension 2 boundary. So this thing has codimension 2. And this defect, this conformal defect, is labeled by the conjugate classes of G. Now, why it's interesting? Because this defect, as long as the symmetry acts faithfully on the local operators of the CFT, you can never scream it. The statement is as follows. You can always take a point operator, say phi, if we're doing free compatibilism, and wind it around this theta direction. You would see that the phi transform will depend on what representation that you are living in. Let's say rho element of G vector of phi. Which means if you live in the real in the infrared, you can always probe the presence of such defect by detecting the branch cut of your 2-point or 3-point or n-point correlation functions. In this way, you can never screen such a defect. Now, I'm going to discuss two particularly interesting examples. You can actually work out that yourself. It's a free theory, so everything is exactly solvable.
Sorry, when you're saying the defect is labeled by conjugate class, do you mean the codimension 1 or the
codimension 2 defect, the boundary of the codimension 1 operator. Which is essentially because you can always create an element from nowhere, let's say H and H minus, and fuse it with the G.
So in that so that this can never be screened?
Yes, this defect cannot be screened, as long as the symmetry G acts faithfully on your local operator in CFT.
Sorry, can you repeat what you said about the branch cuts?
Well, because you can, let's say we calculate the 2-point function of this phi operator, and since this symmetry is non-trivial, it acts by some rotation. Let's say U1 a billion, okay, just some 2 pi alpha basis. Now you can tell me where the defect is by detecting the branch cut of your 2-point function. If there's a point such that wind around it would change the correlation function by 2 pi alpha to the I, then that's where the defect sits. Okay, so you can always do that. No matter what interaction, what deformation you want to trigger on a defect, it cannot be screened. All right?
Sorry, so here by defect, do you mean both the three-dimensional one with its boundary or just the boundary?
Well, codimension 1 defect is topological. I'm talking about the conformal defect cannot be screened. Yes, yes. Okay, I'm going to talk about two simple examples. I have every detail worked out in my lecture note, which I already uploaded to the website. You can do it yourself. It's really simple. It's just free theory calculation. For example, let's take the tau to be the Euclidean time, and again use the polar coordinate. And this monodromy defect, or someone say twist defect, can be implemented by a gauge field background. Here, d mu represents the covariant derivative, and you can couple the free complex Bode to a background such that a mu alpha. Okay, you can check that by the parallel transportation, this phi field indeed, when you wind around theta, from theta to theta plus 2 pi, you would pick up, because of this non-trivial background of gauge field, that phi would transform as, okay? And a similar thing also holds for fermion. The only difference is that you are going to use some direct operators. Let's say psi and d. Maybe some dagger here, I'm not sure. Some dagger here. Again, you couple it covariantly to this fixed classical background of gate field. Let me tell you what you would get if you want to calculate the one-point function, if you want to fix the coefficient here for the current as well as for the stress energy tensor. So eventually, if you do a mode expansion and try to calculate the contribution from each spinning mode for the scalar field, you would have actually found 2 fixed points. And there Cj, I probably don't have time to cover Ct, which means the one-point function of the current. Yeah, in some normalization, this overall coefficient. For the free complex boson, as a function of the flux, you can think of this as a localized flux in the 2+1 space-time. As a function of flux, it's something like this. There is a IR fixed point such that the current becomes identically 0 at alpha equals to 0 or alpha equal to 1, which is actually expected. That means you can turn on no flux or half flux. Both of configuration would preserve the time reversal symmetry, and that will require the current has to be vanished identically. Okay, so this is the IR stable fixed point. That's what you would have found in your experiments if you can, create some lattice model of the free boson. There is also a UV fixed point, which is, I would say, rather unphysical, and the configuration of the current one-point function is such that it is always have a larger current, and the RG flow is such that it always intends to reduce the current. Okay, so that's the physical picture. Okay, why should I do this? The thing is that if you try to do the same for the free fermion, you would find a puzzle. Now let's consider again the same one-point function, Cj, as a function of the flux. Again, I have to apologize that I cannot cover every detail, but you can do it yourself. Everything is free, so that's a classical problem essentially. If you look at the IR fixed point, which means you are doing real physics in lab, this is the curve you would have found, which is actually discontinuous around the half flux. Why should I be bothered? Because I expect the symmetry, the time reversal symmetry, to be preserved at alpha equal to 1/2. However, the current, which breaks the time reversal symmetry, does not approach 0. If I adiabatically tune the flux, you would see that it got diverged. The derivative would diverge depending on which side you would approach the half flux point. Okay, what is the resolution then? This is not, for my standard, it's not acceptable, because you would expect something that is really discontinuous in a continuous real physical world. The solution is that you have to include the UV fixed point, which is the analog of the free complex boson UV fixed point. Sorry, not complex. Free complex boson. And the curve of that fixed point is such that it continues along this line, and it hits 0 when alpha. Sorry, maybe I should change another color. This is the UV fixed point, and it completes the curve. And the RG flow, when alpha is not equal to 1/2, is such that from the UV fixed point toward the IR fixed point. Okay, and you can further verify that when alpha equal to 1/2 exactly, there is an exact defect conformal manifold. So every point along this line preserves the conformal symmetry. There is an exactly marginal deformation you can turn on. And you can do a interesting calculation to see that this Cj function can be interpreted as a topological distance along this exact defect conformal manifold. I think the formula from that, the distance from the Cj equal to 0 is some arcsine function. So this is the topological distance. It is telling you that this defect conformal manifold is not divergent, it's not open. It's a closed manifold with finite volume, which is 2 or 2 pi in some units. Okay. Okay, any question? I have to say sorry that I skipped the detailed calculation, but as I promised, it's just free theory. You just take undergraduate math to do it. Okay. Now, again, if I am an experimental physicist, why should I care about this fixed point, this UV fixed point? As you say, this is not stable along the energy flow. It takes some fine tuning to find this fixed point in a real physical setup. Let's say some lattice at the Dirac point, fixed point. The thing is that if you want to combine these two, this complex boson and this Dirac fermion, into a chiral multiplet of 3D n equal to 2 supersymmetry, you would have found that if I adiabatically tune this alpha from 0 to 1 and stick with the stable fixed point of the bosonic sector, which is this curve, I am actually enforced to take the upper branch of the Dirac fermion fixed point. So here I'm adiabatically tuning this alpha from 0 to 1, and I make sure I stay in the boson fixed point, that is IR stable. Then I would have to do this. I need to come along this way and stay in the upper branch all the way to alpha to 1. That means in the supersymmetric series, if you want to preserve supersymmetry, the periodicity of this flux is actually not 2 pi. Sorry, it's not 1. By changing alpha to alpha plus 1, you do not come back to the same theory that you start with, but instead, you end up with a different DCFT. Okay, what is that DCFT? Why it's so annoying? Why should I be bothered with this? The thing is that you can calculate that at this fixed point, this UV fixed point at alpha equal to 1, there is an operator whose dimension proportional to 1 minus alpha, and it approaches 0. Well, usually when there is a DCFT or CFT has a 0-dimensional operator, that means something is decoupling from this flow theory or the defect theory. And in this case, as I remember, the defect is implemented by this flux, and it is a line defect in the space-time. That means a quantum mechanical degree of freedom is decoupling from this line defect. And what is that? There's a simple trick that, again, I have to say sorry, I don't have time to introduce, but let me just tell you how this formula looks like. So, as I said at the very beginning, you can use this one-point function of the current to obtain the G function, which, as I introduced, is a defect entropy. And the formula is such that, I have 40 minutes. I hope I didn't end up with a lot of confusions. Yeah, so you can do a derivative of G function with respect to alpha, and that is Cj. So that means you can just integrate this curve, and the integration tells you what the G function is for the conformal line defect. And if you do that, you end up at this point, this integral will tell you that G equals to log square root of 2. Log 2, sorry, it's actually log 2. So we have found that when you go back to the same theory, you do not end up with the same DCFT, but instead there is a cubic degrees of freedom that is decoupling with your defect CFT and your bulk theory. Yeah, actually, yeah, that's what I'm going to say about this thing. All right, thank you. Any question?
Any question?
Well, I saw a lot of confusing faces. Okay, if you have any question, please talk to me afterward. And also, I have uploaded every calculation. Every step of this calculation, you can find in the lecture note that I uploaded to your site. I want to make sure everybody understands this. I don't want to play some mathematical fancy things that don't tell you why. Okay, I just make sure everybody follows. All right.
Okay. Thank you very much.
Thank you.